Okay. And then microphone. Speed. Testing the one. Okay, good. That works.
All right. All right. It's my pleasure to introduce Matt Reeves for our next talk.
Thanks. Yeah, so this talk I'm going to give today is essentially about looking at how classical turbulence laws can emerge in the dynamics of quantum vortices in two dimensions, and specifically I'm going to be talking about the Enstrophy cascade in decaying turbulence. Okay, now I probably don't need to labour this point for this audience too much. I'm sure everyone's pretty familiar with the Kolmogorov cascade, but perhaps just for comparison with two dimensions, let's remind ourselves what allows this process to happen in three dimensions, and it's essentially this mechanism of vortex stretching. So if we look at the budget equation for the total energy, and we consider what happens as we lower the viscosity, in three dimensions, what we find is that vortex stretching actually always amplifies the entropy in such a way that we find that the energy dissipation ends up being finite even in the limit of zero viscosity. And it's essentially by realizing that this energy dissipation rate is a fundamental parameter that allows us to go and do this dimensional analysis where we can write down the Kolmogorov law. And we can also, for example, identify a dissipation wave number where the energy will be removed. And from that, we can determine the number of active degrees of freedom in our turbulent flow, which scales with some power of the Reynolds number. Now, in two dimensions, it turns out that since the vortex stretching mechanism is forbidden, it means that the entropy is unable to grow. And the crux of that is that if you consider what happens as the viscosity goes to zero, you find that the energy is in fact has to be conserved. But so what George Batchelor kind of realizes that actually maybe the entropy in two dimensions could do something similar to what the energy does in three dimensions. So in this case, if we lower the viscosity, he said, well, maybe actually the vorticity gradients amplify in such a way that we get a non-zero entropy dissipation rate in the zero viscosity limit. And the kind of picture he had in his mind for this is kind of shown in this picture here. So if we imagine some idealized scenario where we have energy at some typical length scale, what happens is all the same sign vortices want to try and merge, and that keeps the energy at large scales where viscosity can't get at it. But what happens during these merging processes is you also get these long filamentary structures appearing. And so that takes most of the square vorticity to the short scales and also amplifies the gradients in the process. And if you go and do the same kind of dimensional analysis as Kolmogorov, you find that your energy spectrum should scale as k to the -3, or equivalently, you could say that the entropy spectrum scales as k to the -1. They're just related with a factor of k squared. And similarly, you can write down an expression for the active number of degrees of freedom, which you find scales as the square root of the Reynolds number. It turns out there are actually quite a lot of subtle issues surrounding this theory of Batchelor's that created quite a lot of debate. For the purposes of today, I don't really want to get into all that. And maybe it's sufficient to say that the theory does work under some circumstances in two dimensions. And so here's just an example where you can see that this does work in high Reynolds number simulations of 2D turbulence. For a bunch of different initial conditions, you can see that the spectrum, if you multiply it by k cubed, these are all very nice and flat over a very wide range. But one kind of point I will mention as it's relevant for later is this issue of these macroscopic coherent vortices that are very important in two dimensions. Essentially what happens is these very strong, stable structures can sometimes disrupt this cascade and completely swamp the -3 spectrum. And so you end up with a spectrum that's typically steeper than this prediction. And so these were all from different initial conditions, and you can see these structures are very sensitive to what the initial conditions are as well. And just one other thing that I think is worth pointing out is that, so in 2 dimensions, we have this thing where it's actually, there's a very important distinction between whether you consider freely decaying turbulence or forced turbulence. So in this scenario, Batchelor considered that was freely decaying, you just get this -3 spectrum. Whereas Robert Kreisman realized that actually if you consider a kind of ideal scenario where you're forcing your 2D turbulence, you can simultaneously get this Enstrophy cascade, and you can actually recover this -5 third spectrum, provided the energy cascades backwards in wave number. So that's classical fluids, but we've also known since kind of the late 90s that quantum fluids, and in particular superfluid helium, can support the Kolmogorov cascade. And that was shown in this nice experiment by Mora and Turbulence. And they showed that essentially you get this -5 thirds law appearing regardless of what the superfluid fraction was. And it turns out that this thing persists even down to when you have essentially 100% superfluid fraction. And the other thing they found is that actually the Kolmogorov constant associated with the cascade doesn't seem to depend on this either. And the kind of understanding we have of it these days is nicely summarized in this picture by Carlo and some of his co-workers, where basically if we have a large number of quantized vortices of same sign and they're bundled together, then the bundles start to behave in a semi-classical way that can mimic a classical fluid. Now, in more recent years, there's been quite a lot of developments in ultra-cold atomic gases, particularly atomic BECs. And so we now kind of have these systems that are very large and oblate, so we can study the dynamics of many quantized vortices in the kind of 2-dimensional framework. And we've already seen earlier in the week that some results where we've started seeing analogies popping up with classical fluids. For example, in the talks by Chris Halmison and Tyler Neely, showing that you can get these macroscopic flow structures emerging that are associated with negative temperature states of vortices, as was originally predicted by Onsager. And just a couple of other examples, because I think they're quite neat. There was this paper out of Newcastle from last year showing a proposal to look at the Kelvin-Helmholtz instability in an atomic BEC. I'm sorry, you probably can't really see that on the screen. And another nice one was this study by Sasaki et al. Looking at the wake of a cylinder and in a 2D condensate, and they found that you actually got a superfluid analog of the von Karman vortex street, where the components of the street are these pairs of same sign quantized vortices. And they also saw you got this V-shaped wake of dipoles, which seems to have no classical analog. And the group at UQ have actually been doing some preliminary work to try and see if they can observe these. So you can see the V-shaped one there, and it's a bit of a messy vortex street there. But here you can see there's kind of a semi-classical vortex street emerging there. So thanks to Tyler for those images as well.
So in these images, the velocity is changed?
That was actually different size obstacles, I think, for those three. Is that right?
Yes, mostly that. Yeah. Slight differences in loss.
So now, given all these kind of similarities popping up between quantum and classical fluids, one might naturally ask whether in these atomic gas systems, whether you could see any of this classical cascade physics in these systems. And it turns out a lot of people have actually done some work on working out whether this inverse energy cascade could appear in these systems. One of the earliest examples was this paper by Angela White and Carlo Berigni, where they looked at what happens if you just continuously force an atomic condensate with some kind of stirring potentials, and they were looking for aggregation of same sign quantized vortices associated with this inverse energy cascade. And sort of, unfortunately, what was kind of quickly realized is that these atomic condensates just simply don't really have the accessible range of length scales to see this kind of physics, because the typical intervortex spacing is maybe something like 10 Healing lengths, and the macroscopic scale of the system is maybe 100. And this is in stark contrast to what you see in superfluid helium, where there's an absolutely huge range of length scales between all these things. And a further complicating factor is that often these systems are harmonically confined, so you have a non-uniform density that kind of adds in complications as well. So then some other people, including myself and co-workers, decided, well, let's not worry about whether this can be realized in a real system yet, and let's just see if we can see it in an idealized system. So we looked at GPE simulations in a large uniform system, looking at turbulence generated by a grid of steering obstacles. And we were able to see some signatures that you would expect if you were seeing in one of this inverse energy cascades. So we saw like an aggregation of same sign vortices making larger and larger flow structures. And there's some indication of a -5/3 scaling in the energy spectrum, albeit over a somewhat limited range. And there have been there's been some more recent work looking at this in a force point vortex models as well. And again, you see this kind of macroscopic flow structures emerging. But similarly, I would say in both of these, the spectral scalings you see are not exactly ideal. And another kind of interesting issue is that in all these studies, there only seems to have been one attempt to look at the constant associated with the cascade, and that was actually done quite a while ago by Seguier and Aref, this force point vortex model. And they actually ended up finding that the constant associated with this cascade was 14, which is absolutely huge, even compared to the accepted value, which is 7. And that result really seems to be at odds with what we know from the helium results, where the constant is the same across quantum and classical fluids. So there seems to be a bit of evidence for this inverse energy cascade in 2D quantum fluids, but perhaps it could be clearer. But basically, nobody seems to have looked at this Enstrophy cascade at all. And so I thought it would just be interesting to see if this phenomenon could emerge in quantum systems. And so there's interesting questions around, well, like how many vortices do you actually need to see this classical physics emerging? And then once you know that, you could make some informed statement about, well, could you ever see this kind of physics in a real atomic BEC or some other kind of 2D quantum fluid system? And even if it turns out the answer is no, it would be maybe good to know that there's this connection here, because it's kind of just like these cascade theories kind of give you a fundamental basis of understanding for the turbulence in these systems. So we thought, and maybe to sidestep all these issues where you have to design some kind of forcing carefully to look at this inverse cascade, let's just look at the Enstrophy cascade that Batchelor talked about in the decaying case. So you can just set up a system and let it go. So the kind of system I've got in mind is some just kind of large uniform atomic BEC or some kind of similar system, which you could model with something like a Danish-Gross-Podevsky equation. But it turns out that's actually, for the system sizes you need, that's both difficult and kind of unnecessary, because you can actually move into a picture where you just look at the dynamics of the defects or the vortices. So this is, as was actually shown in Tapio's talk, you can just look at the dynamics of the vortex positions, which is expressed entirely in terms of the gradients of the phase and the density of the condensate wave function. And since I'm considering a uniform system here, you only have to worry about the phase gradients. And then we can kind of maybe go an extra simplification and say, oh, well, let's forget about the sound waves as well for now and just treat the vortex dynamics as quantized point vortices. So to borrow the analogy from Carlo's talk, we're not going to worry about any of the bark. We just want to look at the trees. And then we can worry, maybe we can go back to the details later. So we've got this, this standard point vortex model. And we're going to go and do what you usually do when you want to look at these cascade theories and forget about the complications introduced by boundaries. So we're just going to look at our system in a periodic box. We can go ahead and write down an expression for the vortex velocities in terms of all the vortex positions, which is somewhat complicated, but you can write it down. And we can also write down an expression for the kinetic energy spectrum. I'm just going to draw your attention to the fact that there are two terms here. There's the self term that only depends on the number of vortices and actually doesn't tell you anything about the spatial structure of your vortex distribution. And then there's this interaction term, which actually does tell you about that. And it turns out this term, at least in 2 dimensions, is essentially irrelevant. And we'll see that if you included it, it actually obscures your results. We can also go and look at the evolution of the energy spectrum, which we can, from our conservative and dissonant parts here, we can assign a transfer function, and then from that we can look at the fluxes in wave number space. Now, even though this approach is a bit simpler than looking at a full Gross-Vitebsky model, it's still kind of computationally challenging because calculating the vortex velocities is an all pairs n body problem, so that scales rather poorly as n squared. And in fact, calculating the fluxes is worse and scales as n cubed. But nonetheless, this can be done, and so to kind of do this up to large vortex numbers, we just wrote all the codes to run on graphics cards using CUDA. Okay, so the other thing we want is to make some kind of really idealized simple initial condition, which for quantum vortices is actually not obvious how you would do this initially because they're localized objects, so they have a very broadband energy spectrum. But it turns out there's a reasonably simple trick, which is you just make a corresponding classical vorticity field in wave number space. So you populate some shell, you transform that, and you get something that has some characteristic flaws like this. And then actually you just use that thing as essentially a probability distribution to the rejection sampling for your quantum vortices. And then when you look at the spectrum, you calculate, you find you get exactly what you want. There you can see there's a self term that goes like 1 on k. And then there's a big spike at the wave number we've chosen for the interaction bit. And again, we're going to see that we actually really want to ignore this bit. So now let's see what happens if we take this setup and evolve it for a fairly large number of vortices. We've got 512 of them, which would be hard to put into a condensate, but never mind about that. And this is what we see. So you can't really see too much going on with the vortex distribution here, nor can you see much going on with the fluxes, but you can see that the energy spectrum does seem to develop this k to the -3 law. It's not over a huge range, but it looks like this might be the thing we're looking for. And I'll just point out there, I've only plotted that interaction bit there, and what we actually found is if you included the full spectrum, you couldn't see any of this at all because it was completely swamped by that 1 on k behavior.
Excuse me.
Yep.
-3 law, it's a trivial result from the velocity around.
No, this is not because of that. So yeah, you do get, if you do GPE simulations and you look in the core, you get a -3, but that's just completely associated with the core of the vortex. This is all due to vortex interactions. So now let's just go completely crazy with this, see if we can get really clear signatures of this thing. And if I'll just, that ran much better on my computer, but. Anyway, here you can see everything's a lot clearer. There's all that filamentary structure I was talking about, and there's a huge range that agrees pretty well with K to -3. And we can see that there's a nice constant flux of the entropy towards the small scales here. So that was kind of the general picture we saw, starting from this idealized initial condition. Then you get this this filamentation of the vorticity field starting, and there was actually a transient regime where we saw this -4 scaling that was predicted by Sackman. And then as the turbulence matures, you see this, as these filaments are stretched and packed, this -3 law emerges, and you can see there's a roughly constant flux there as well. And then at late times, we see that the spectrum eventually collapses and the turbulent flux is all gone. There's nothing really being moved around in scale space anymore. And there's just a few of these coherent blobs of coherent vortices lurking around. Now, something else we were actually able to look at with this was trying to extract the Cascade constant. So what this graph is showing is that compensated spectrum for a varying range of vortex numbers, and so we've just multiplied by k cubed and divided by the corresponding appropriate power of the flux. And so these are for the different numbers, and we've just shifted all these curves vertically for clarity. And this horizontal line in each case is the value 1.6, just for reference. And so you can see up at where we have rather small vortex numbers, we still have some range of flatness here, but the constant is actually quite large, so that's suggesting when you don't have many common vortices, you're getting inefficient transport through scale space. But then as the larger the constant is, that's basically telling you the less efficient the cascade is. But then as we crank up the vortex number, it looks like these spectra seem to converge onto this value that's 1.6, which is actually in pretty good agreement with the accepted classical value, which it varies depending on what your initial conditions are, but it's sort of in the range of 1.1 to 1.4. And the other thing we were able to see in here quite nicely is that the spectrum just suddenly drops off when you get to the wave number associated with the inter-vortex distance, which of course makes total sense. You're going from a regime of multi-vortex physics down to the scales where you're recovering single vortex physics. And yeah, so that just scales as square again. And it turns out you can actually understand this increasing of the range of length scales in terms of this superfluid Reynolds number that was actually originally introduced by Onsager in a conference proceedings, and he seemed to never write it down anywhere again. But it is discussed elsewhere. For example, in this, there's quite a nice discussion about it in this paper by Bolovic. And what Onsager said is, well, actually, maybe you just have to replace the viscosity with the quantum of circulation, which is the only parameter around that has the right dimensions. So you can think of this thing as kind of comparing what the macroscopic flow structures compared to just what you get for a single quantum vortex. So in the case of our system, we can say, well, the characteristic velocity is something like the square root of the interaction energy, and the length scale is just the inverse initial wave number. And then we can go ahead and do some kind of write down what the interaction energy should be based on some dimensional arguments. And you find that there's some dimensional parameters, and then we could, based on the form of the equations, we can say this should scale something like n squared and something like the inverse initial wave number squared, and then any deviation from that we could vary in some arbitrary function I'll call A. And then it turns out if you go and calculate this the energy for a range of these delta functions, initial conditions we looked at, it's essentially constant. There's no real clear trend here. As long as you have many vortices in each cluster, it doesn't change very much, and it's roughly a quarter. And so what that means is that the superfluid Reynolds number is basically the number of vortices divided by the initial wave number squared. And if you replace this with the number with the definition for the average intervortex distance, you find that the ratio of these wave numbers is exactly the square root of this parameter, which is exactly the same as what you get out of the classical result in the bachelor theory. And then after I found this result, I thought, well, has anybody seen this in superfluid helium as well? And it turns out they have. So there was this experiment from a few years ago where they inferred the average intervortex distance from measurements of the total line density. And then when they plotted all the measurements against this superfluid Reynolds number, you can see it scales exactly the way you'd expect for the dissipation length scale in the Kolmogorov energy cascade. Okay, so it's actually only one other thing I wanted to briefly talk about, and that was coming back to this issue with the coherent vortices. So basically, it's well known that this Enstrophy cascade can be a bit sensitive to the initial conditions. So we just looked at a couple of different setups to see how the initial conditions affected these results. And here we're looking at actually a lower energy situation where we've got smaller initial clusters. And in this case, we actually see that we get this -3. -3 seems to survive for actually kind of the entire duration of the simulation compared to the previous one I showed you. And if we compare that with a really high energy situation where we have a really kind of spatially intermittent initial vorticity distribution where we have all these Gaussian blobs, and we run that, you can see that even though there's quite a bit of this filamentation going on when these vortices get ripped apart, the spectrum doesn't resemble this -3 law at all, which is kind of what we were expecting. So this is just to compare kind of what you get in the kinetic energy spectrum, looking at the linear fit to the spectral slope in log-log space, and looking at the fit quality. So you can see in that first case I showed you has good agreement with the -3 for the first half, and then it kind of collapses after that. The second one, where we had a lower initial energy, it actually agrees for the entire duration. And then for this really high energy case with the Gaussian clusters, even though you get a really good linear fit over the whole range, it varies somewhere between -5 and -4. I've kind of raced through all that, but so to conclude, I hope I've convinced you that it's pretty clear that a 2D quantum fluid could support an Enstrophy cascade, but based on the results we saw, it kind of seems like you need at least a few hundred vortices before you can really say, oh well, no, I feel like I can trust this scaling I'm getting out of the spectrum now. And so based on that, we can do a kind of order of magnitude estimate of how big we'd expect the BEC to need to be able to see this and not invalidate that point vortex approximation we made. And it turns out you need to have a system that's something like 800 by 800 healing lengths, which is, it's pretty large, but to be honest, going into this, I was expecting to get a way worse result than that. For comparison, the BEC that they've got at UQ, this in the DMD, is 200 by 200. And finally, I'll say that given the results we got for this with the cascade constant, it certainly seems like maybe it would be worth revisiting the inverse cascade, because it seems like it should be possible to recover all the classical results from that as well. And that's all.
All right, questions?
Yes, Carl.
To make the connection with the actual C experiment,
Yeah.
well, you need to include regulations.
Yes.
So that is easily done in the point vortex model by setting like a distance. So have you ever tried, and what happens if you?
So I did actually have that included in the simulations, but basically I kind of ended up choosing the box size so large that it didn't matter. But I do think it would be good to go and look at that because, you know, vortex, anti-vortex annihilation is kind of does exactly what viscosity does in classically anyway, right? It pulls out some vorticity but removes basically none of the energy, at least when you have a distribution that's kind of like this. So I think that would definitely be worth looking at in more detail.
Can I ask you about the inverse energy cascade?
Yep.
So if you make the system bigger and bigger, do you think the inverse energy cascade occur in 2D quantum turbulence? So if you said the inverse energy cascade cannot clearly resolve in a 2D quantum turbulence because the system is not so big.
Yeah, I think it's just an issue of having a large enough system. I think that's all it is. So you know, there's this problem where you have to keep driving it to sustain the cascade, and then you run into this issue where you need larger and larger scales, and then everything gets slower and slower. So it's just a really challenging thing to look at numerically.
So this is related to that question. So here you were looking at the direct Enstrophy cascade. So, do you have any signatures of the dual cascade, simultaneous Enstrophy cascade and energy cascade? I'm wondering whether it would be, so you're looking at the decaying case here, but couldn't you pump in, repeat your initial condition by adding every now and then, adding new vortices at precisely at the K vector that you chose?
Yeah. So
the question is, just in case, can you somehow drive the system pumping in energy at the K vector so you see both cascades in these 2D systems?
Yeah. So we actually suggested that at the end of this paper. We just haven't got around to trying it yet, but that was exactly the idea: is take this rejection sample thing and just throw those in periodically, which should give you this really idealized localized forcing, which might help make this all clearer.
Thank you. So my question also relates to that question. In classical turbulence of 2D fluids, you have essentially, as far as I understand it, you have the entropy state in order to carry away the angular momentum. So if, for example, the big whirl in Jupiter spins up, you need to have opposite angular momentum to be transported into the tails of these wings. Yeah? And this makes kind of the entropy cascade. Now, in these systems, you don't have these as you see it so small. At the same time, you know that a K to the -3 you have for a single vortex due to the core structure of the vortex. Yep. So if you now cluster your vortices to these kind of macroscopic vortex-type objects, shouldn't one rather interpret that the K to the -3 of arising from this clustering of cores, which themselves already produce a K to the -3? What's your opinion on that?
No, so everything that's being shown here is entirely due to the distribution of the vortices, and so the -3 that you would get in GPE relies on you putting the core structure in, which you can do in this because we know the analytic structure of the core. But here I've just completely neglected.
No, I know, but the way sort of these then cluster, so it's a question of the spatial distribution of these points. Essentially, you can't solve the core. I know, you don't have it in here. Yeah. But the way how they cluster, so their distribution makes again the same power law.
Yeah. But it's
but
a completely
not
different
the same as
reason.
you have in these kind of classical configurations.
No. So this is the same as classical.
I guess the point here was that that picture that you put there, you replace every yellow block with a single vortex with multiple charge. As actually replace these distributions by single vortices, but give them multiple charge, and then look at the configuration then.
But I mean, then you would lose all of this spatial
Oh,
structure.
these are different. Yeah.
Right. Well, yeah, there you could.
But this
And you
is
probably get the same result because those are kind of behaving like single clump things here.
One quick question. I didn't understand your comment about using E interaction instead of the total energy. I mean, the argument for the cascade was for the total energy, right?
Yes. Where is it? I'm not sure I can give you a clear. And so this is that part. So if you wrote down the, like, if you move this into position space, I think this is the bit that would give you the point vortex Hamiltonian, and this is basically when if you write down the Hamiltonian as the logarithmic interactions. This bit you'd normally throw it away because if you integrate overall K, it diverges anyway, right? It's an infinite constant. So it's just that you pretty much always see this thing be included in spectra, and it was by trying to look for this really steep power law, I realized actually there's no reason to include this because it tells you absolutely nothing about the spatial distribution. It just tells you how many vortices you have.
But I mean, then this would be a problem also for a GP simulation.
Yeah, that's exactly right. And I mean, so what you can do instead is actually just look at, maybe I can go to an extra slide I have. You can actually just look at 2-point vorticity correlation functions instead, because they just map with a Hankel transform, and you get the same thing in the 2-point vorticity. You get this singular part R equals 0, which is the corresponding bit of the self energy, if you like, and that it doesn't tell you anything.
Okay, any final questions? All right, thank you very much.